Good morning, everyone. I'm going to allow another 5 minutes or so for people to zoom into our class. So please bear with me.
I can't hear this guy. Speak up, white man. Teach me your knowledge with your infinite degrees. This man said degree style. He said white man style, $200 for 5.
Well, good morning, everyone. Something interesting happened over the last week. Last Tuesday, we had 24 people in the class, and now we have 37. So we've had a lot of people join since Tuesday and Thursday. So I'm going to once again just briefly go over our course website for the benefit of those students who have joined since Thursday. And there's, as I mentioned, a substantial number who have. I'll switch over to our course website. So here we have our course website, and in the Start Here folder, you'll find the Zoom meeting invite and a link to e-learning resources, syllabus, and schedule. The schedule has the material, the readings that you'll be doing, the lectures that we'll be covering on specific dates. And the syllabus has information such as the textbook. We're using discrete mathematics by EP and the grading method and so on. In course materials, we have things like our lecture slides, and today we'll be doing lecture 3. Last week we covered lecture 1 and lecture 2. Also, we'll have videos. So I began recording the videos on Thursday. So we have Chapter 1, Section 2 as a video. And I'll post Chapter 1, Section 3, the video that we're doing today, hopefully sometime tomorrow. Under assignments, we have 2 elements. Let's see if I can get in that one. Okay, there we go. I'll restart this particular page. There we go. We'll go to assignments. And there's 2 elements in assignments. The first is exercises. And the exercises aren't graded. They're just material that is at the end of the chapter, at the end of each section. And it's things that will, if you keep up with them, you'll know that you're keeping up with the material that we need to cover in the class. So these are exercises. Again, they are ungraded, but they're there for your benefit to just make sure you're keeping up to speed. Homework assignments are graded. And so we have a homework here, homework 1, and we do have a grader, Ab Hiram, and I have his email in the homework. And you'll email your responses to Ab Hiram as you complete each one of the graded homeworks. And if we look at the schedule, so today, you'll note in the schedule, we are covering Chapter 1, Section 3, Relations and Functions. Homework 1 is assigned, and it will be due on next Tuesday, the February 9th. Okay, any questions on the course website? Okay, very good. Well, let's go on with our lecture then. And as I mentioned, we'll be covering relations and functions today. And as we talked about last week, there's different ways in which elements in two different sets can be related. We can use traditional relational operations such as less than, greater than, or equal to. And likewise, we can come up with more complex mathematical equations that we can use to relate things together. So just as an example, let's look at two sets. The set A that has elements 0, 1, and 2, and the set B that has elements 1, 2, and 3. And so we're going to make a relation up that states that they are related according to our rule if x is less than y. So we have the ordered pairs x less than y. So we use that notation and we take each one of the elements in our first set, which is A, and we'll match that to each one of the elements in the second set and see if the relationship holds. And so here we see those cases where it does hold. 0 is less than 1. So it's in our relation. 0 is less than 2. 0 is less than 3. So you can see we took 0, the first element in A, and we matched it with each of the elements in B. Next, we take the element 1 in A and match it with each of the elements in B. And we find that 1 in A and 2 in B are in the relationship according to our rule. And so are 1 and 3. And the same thing with 2 and 3. Now, some of the element ordered pairs are not. So 1 from set A and 1 from set B are not related according to our rule because 1 is not less than 1. And likewise, 2 from set A is not related to 1 or 2 for the same reasons. So we take the Cartesian product of A and B, that's noted as A cross B, and that's going to be the set of all ordered pairs whose first element is in A and whose second element is in B. And we denote it with A cross B equals our curly braces for the set notation, the ordered pairs X and Y, such that X is an element of A and Y is an element of B. And again, we went through the A cross B for our particular problem that we just looked at. And this is the set of ordered pairs we get for A cross B. So the elements of some of the ordered pairs in A cross B are related according to our rule. And that rule was X is less than Y. And so these are the pairs that we found in doing our analysis that are related according to that particular rule. That's the set of ordered pairs at the bottom of this slide. So the relation itself can be thought of as the totality of all ordered pairs whose elements are related by some given condition. So we say a relation R is a, from A to B, is a subset of A cross B. And you get any ordered pair, it's related, X is related to Y, only if the ordered pair XY is in R. In other words, it satisfies the condition that we used, or the filter that we used to add things into the set. So the set A is called the domain of the relation, and the set B is called its codomain. So here's some notational information. XRY means that the ordered pair XY is an element of our relation. And remember, the relation is a subset of the ordered pairs from A cross B. The notation X not Y means that it's not related. So in other words, the ordered pair doesn't satisfy our condition, and therefore it's not in our relational subset. Okay, let's look at our understanding of this. Go ahead and take a few minutes to answer these questions, and then we'll go over them. Okay, let's take a look here. Okay, can everybody see the whiteboard? Okay, very good. So as we can see, A cross B is going to be the set of ordered pairs 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, and 2, 3. 1, 1 is an element in R, because 1 minus 1 divided by 2 equals 0 over 2, which equals 0, which is an integer. 1 minus 2 is not an element of R, because 1 minus 2 divided by 2 equals minus 1/2, and that's not an integer. 1 3, the ordered pair 1, 3, is an element of R because 1 minus 3 divided by 2 is equal to minus 2 over 2 or minus 1. That's an integer. The ordered pair 2, 1 is not, and that's because that is going to resolve to 1/2. 2, 2 is equal to 2 minus 2 over 2 or 0. So that's an integer, that is an element. And 2, 3 is not an element of R because 2 minus 3 is equal to minus 1 over 2. So that's minus 1/2, that's not an integer. Okay, let's come back to our slides. So then the question is 1, 3 in our relationship? Is 1 related to 3 according to our rules? And the answer is yes, it is. Is 2 related to 3 according to our rules? And the answer is no. And the last one is 2 related to 2, and the answer is yes, because that resolves to 0. Okay, and then finally, question C, what are the domain and codomain? The domain is the set with the elements 1 and 2, and the codomain is the set with the elements 1, 2, and 3. Okay, any questions on that?
Yeah, how do you, can you hear me?
Hold on. Let me tell you what. It's probably better if you type your question in chat, because I get a reverb when you know, the audio comes in. So if you have a question, please type it in chat. Well, the domain and the codomain are going to be the two sets that are involved in the relationship. So in this particular example, the set A has the elements 1 and 2, and that is going to be the first part of our ordered pair. So that becomes our domain. The set B has the elements 1, 2, and 3. That becomes the second part of our ordered pair, and that becomes our codomain. Okay, any other questions? Okay, let's go on. So we can also draw what's known as an arrow diagram for a relationship as well. So the way we do that is for each element X in the set A and each element Y in the set B, we draw an arrow from X to Y if and only if X is related to Y by our relationship. So we can then tell some things quickly by looking at those arrow diagrams if things are related. So we can draw an arrow diagram for the set A equals 1, 2, 3, and the set B equals 1, 3, 5. And we have two relations. XY is an element in AB if X is less than Y. That's for S. And then the other one is T, which has the relationship defined by the ordered pairs 2, 1 and 2, 5. So spend a minute and draw some arrow diagrams for relation S and relation T. Okay, let's take a look at these. Okay, can you see the whiteboard? So here we have the relation S, which is defined as X is less than Y. So we take the elements from our first set and compare them with the second, and 1 is not less than 1, so that's not included, so we don't draw an arrow. But 1 is less than 3, so we have an arrow from 1 to 3. And then likewise, 1 is less than 5. So we have an element going from 1 to 5 as well, an arrow going from 1 to 5. 2 is not less than 1, so no arrow there. But 2 is less than 3, so we have an arrow. And 2 is less than 5, so we have an arrow. Finally, we have 3, which is not less than 1 and not less than 3, so no arrows there. But 3 is less than 5, so we have an arrow going from 3 to 5. And for relation T, we had the set of ordered pairs 2, 1 and 2, 5. So we have 2 arrows coming out of 2, 1 to the element 1 in set B, and 1 to the element 5 in set B. Okay, any questions on the arrow diagrams? Let me go back a little bit. Yes, the domain is the first one. Yes, Joy, it is coming up. Yeah, X is coming from A. Yes. Okay, let's share. Let's go back to our lecture. Yeah, let me finish the lecture and then we can certainly do another one then. Okay. So the next topic we want to go into is functions. And they're a special type of relation. So they're a relation where if you have an ordered pair, that x and y that are in the relationship F, and you have another ordered pair x and z that are in the relationship F, then y is going to equal z. So in other words, every element x in A, there's only one element y in B that satisfies the relation for F. So they give two properties here that indicate the nature of a function. For every element x and A, there's an element in the y in B such that the ordered pair x and y is an element in the function, which is a special type of relationship between x and y. And then the second property is for all elements in A, x and A and z and B. If x, y are in F and y, x, z are in F, then y is equal to z. So properties 1 and 2 can also be stated as a relation F from A to B is a function if and only if every element of A is the first element of an ordered pair in F. So you can't have any elements of A not participate. And the second is no distinct ordered pairs in F have the same first element. So in other words, you can't have more than one pair with a unique first, with the same first element. So we note that here, and the notation for a function is f of x, where you have the function f and you've got parentheses for around the variable x. So here we have a chance to do a little more with arrow diagrams, Kamsi. So we'll do some here. Let's take a minute and look at these. We have two sets, the set A with the elements 2, 4, and 6, and the set B with the elements 1, 3, and 5. And so which of the relations R, S, and T, R is in A, S is in B, and T is in C, are functions? So go ahead, let's take a look at that one. Well, R is not a function because it does not satisfy property 2. It satisfies property 1. Every element in A is related to some element in B, but it doesn't satisfy property 2. In other words, we cannot have two ordered pairs with the same first value. And in this case, we do 4 and 1 and 4 and 3. They have the same first element, and they have different second elements. So that means they are not a function. And we can see this graphically just by looking at the arrow diagram. So going back to the definition of A, we have just the ordered pairs 2, 5, 4, 1, 4, 3, and 6, 5. So we draw an arrow from 2 to 5, here 2 to 5, 4 to 1, 4 to 3, we draw an arrow, and then 6 to 5, we draw an arrow. And we see we've got 2 arrows emanating from point 4. That's another giveaway that it's not a function. Okay, any questions on that one? Okay, let's look at B. We'll do arrow diagrams again. So B is for the relation S. S is not a function because it doesn't satisfy property 1. So that means it's not true in this case that every element of A is the first element of an ordered pair in S. So 2 will map to 3 according to our rule, 4 will map to 5, but 6 would map to 7, which is not in set B. So here we violate the first rule for a function. Every element in A has to participate in the function, and 6 is not. And then finally, C was just this arrow diagram right here. And a T is, in fact, a function. Each element in the first set, 2, 4, and 6, is related to some element in the second set, 1, 3, and 5. And no element in 2, 4, and 6 is related to more than one element in 1, 3, and 5, the set B. So we only have one arrow coming from each of our elements in A. In other words, we don't have A with the same value participating in 2 ordered pairs. They're only in 1 ordered pair in the relation, and that makes it a function. And we note that here. Okay, so are there any questions on of the definition of a function? Okay. So a lot of books talk about a function machine. And a function means that you always get an output for any given input into the machine, and you get a specific output for a specific input. In other words, if you give it one specific input, you're not going to get 2 outputs, you're going to get 1 specific output. And also, every element in the first means that it's going to be in the second. The E means it's an element of. So when we say X and Y are an element of F, remember, F is a relation, and a relation is a set of ordered pairs from the cross product of the 2 sets. So the notation big E, or it's actually a Greek letter epsilon, which corresponds to the big E, that means it's an element of. So that means that this particular ordered pair is part of the set of ordered pairs in our relationship. In other words, this set of ordered pairs this ordered pair satisfies the conditions that we put down for the relation. You're welcome. So we have a common function. It's the squaring function, where we go from f, and that's a relationship on real numbers to real numbers. And it's defined by the formula f of x equals x squared for all real numbers. And there's a couple of other notational equivalents. A big dot squared is one, and then x arrow to x squared is another. And a successor function is where we're just going to be adding 1 to the current element. So no matter what integer is substituted for n in the function g of n, the successor function is going to add 1 to it, which it can also be denoted by the big dot plus 1. So in other words, g sends n to n plus 1, as we see here. And finally, we have a constant function where no matter what r is, it's going to result in a constant value. And here's some examples of function machines for each of those. So a function, again, is any entity that can be thought of as a special relationship, and it has an input-output machine that operates according to certain rules. And this is the reason why a function is generally denoted by a single symbol, such as f, g, log, or sine. And again, just as a reminder, a relation is a subset of the Cartesian product of ordered pairs between two sets, and a function is a special kind of relationship that satisfies two rules. The first rule is that every element in the first set, A, is part of an ordered pair in the relation. And the second is that no two distinct ordered pairs in F have the same first element. Okay. So here we have some examples. If f and g are functions, and f of x and y is an element of the cross product of a and b such that y equals f of x, and there's another function g, again on the domain of x and y, the set of ordered pairs in the cross product that are elements of the cross product of ordered pairs a and b, such that y equals g of x. Then we can check for the equality between f and g. And if f equals g, in other words, the function f equals the function g, that's true if and only if f of x equals g of x for each one of the x in the set A. Okay, so again, we would look at each of the ordered pairs in f of x and g of x and determine that the values where we have for each specific value of x, both f of x and g of x yield the same value of y. Okay, so let's take a minute and look at these particular problems. Now, one thing I'd like to mention is that the notation for the square root of some squared value is typically meant to mean the positive square root. And then if you wanted it to be the negative square root, you'd put a minus in front of it. So just like we have, like the number 3 would be considered a positive 3, we don't have to put the plus sign in front of it. But if we wanted to designate like a negative 3, we'd have to put a minus sign in front of the 3. So that's the notational convention that the author is using in the book. So when we see her put the square root of something without a minus sign, she's meaning the positive square root of that particular value. Okay, so with that in mind, the question is, does F equal G? And the answer, of course, is yes, because the absolute value of any real number is going to equal to the positive square root of its square. And we see that here. So again, F is equal to G because for each particular X, F of X is going to be, which is the absolute value of X, is going to be equal to the positive square root of X squared. Okay. So any questions on what we covered in terms of relations and functions today? Okay, well, let's take a quick look. Homework 1, as I mentioned at the beginning of class, is assigned today, and it will be due a week from today, Tuesday the 9th. And again, it's on our Blackboard course site under assignments, the folder homework. And you'll see homework 1, and just follow the directions in homework 1. The email for Ebe Hiram is in, oops, where's my marker, sorry, is in the homework itself. And it'll cover some of the material we've had in Chapter 1. We're finishing up Chapter 1, and then next week, on Thursday, 2 days from now, we're going to begin Chapter 2. And we're going to start looking at logic. And so this is something most of you probably have had some experience with, especially in your programming classes with regards to Boolean algebra and conditional statements, logical form, and so on. But we're going to be going into it in a formal way in Chapter 2. Okay, any questions? We can definitely go over homeworks in class. I'm going to wait for Ebe Hiram to tell me Ebe Hiram tell me when everybody's got the information in, and then we'll definitely go over it. And regarding the quizzes, there aren't going to be any quizzes. I'll pull up the syllabus and we'll go over grading. Again, as I mentioned to everybody, last Tuesday, I had probably 24 people in the class, and then by Thursday, it had gone up to like 29. Now I have 37. And so we briefly went over some material at the beginning of class. Let's go ahead and do the syllabus. So just to level set everybody, and you turn your homework in by emailing it to Ebe Hiram. He's our grader, and his email is in the homework itself. And I will also send out an email reminder. I think I already did, but here's the problem. I sent that out last Tuesday and we only had 24 people in the class. So I'll send it out again because, as I mentioned, well, as of yesterday, it was up to 37. It may be even more. And I had, people emailing me saying they're joining the class. And, those of you who have joined, just catch up with the readings. And I am the class and I did agree to start recording things. And so I put a recording of Tuesday's lecture up. I'll put today's recording up as well. So you can always look at that as if you need to. But let me switch shares right now and get over to the syllabus for the new folks. So this is our book. It's by Susanna Epp. It's called Discrete Mathematics. It's a standard text in major universities across the United States and around the world. We're covering this material, relations, functions, logic, proof methods, induction, matrices, sets and sequences, and directed graphs, and so on. So that's the material we're covering. Now, in terms of your grading, there won't be any quizzes. You're going to have 6 homework assignments. Each of those is worth 5%. So that will be 30% of your grade. A midterm exam will be worth 30% of your grade. And then the final is worth 40% of your grade. And we will be having, so someone asked if we'll be having a review. And yes, indeed, we'll have a review before the exams, and we'll have review slides that will include for your study purposes. So again, welcome to all you folks that joined the class in the last week. And I think you haven't missed anything when I will be going forward together. It's going to be focused more on what we learned after the midterm, but obviously we build on everything. So, parts of chapter 1 are important in chapter 10. And so on. So it's kind of, you build the foundation brick by brick. And so you can't not have the bricks that you went over at the beginning and still have a grasp of what's going on at the end. But in terms of problems, they will be focused more towards what we did at the end in the second part of the semester. Okay, any other questions? You're welcome. All right, see you guys on Thursday then. Okay, thank you. Okay, thanks. You too. Thank you. Thank you. Someone did set up a group me. And I think they even put it in the chat. Let me see if I can find it. Yeah, here it is. I'll post this down below. Yeah, there it is. Perfect. Thank you, Hassan. Okay, see you guys on Thursday.